everybody. Hello and welcome to this webinar at OPIT. Thank you for joining. My name is Greta and I'm here today with my Professor Maha. We're going to just start in a second. Okay. So today we're going to talk a little bit about OPIT, and then Professor Maha will just have a presentation about the deep kernel method. So she will show an example of advection-diffusion reaction. And you're very welcome to ask any questions. Maybe at the end is better. But now just 2 words about us. So Maha Youssef is professor at OPIT and also professor in general mathematics, and she will explain this method. And my name, as I said, is Greta. I'm head of marketing and admissions. OPIT is an institution whose main mission is to unlock progress and employment on a global scale. We want to provide tier 1, top quality, and affordable education in the field of technology and computer science, data science, cybersecurity, digital business, data science, responsible AI, so artificial intelligence as well. What OPIT stands for and what sets us apart is really that we are an institution that is fully accredited at the European level, and also we are recognized by WES in the US and Canada. Our programs are totally online, very flexible, so you can join by anywhere, wherever you are. You can work and study at the same time. As I said, we are very focused on technology, but also our programs are aligned with what is required today career-wise. So we've designed the programs with companies and for companies. Despite the fact that we are online, the support is also always available. We have tutors every day of the week. You have a co-pilot every minute of your life. You have the program coordinators, the career service, the professor. So they're very much available. And finally, we believe to be inclusive and at the same time affordable. One of our key strengths is our professors, our faculty. So we have a faculty that is a mix of business people and professors. They're very much qualified. They're very good at teaching, and they come, as I said, also from business. Like for instance, Professor Zorina Liata, she's principal AI and generative AI at Amazon. We have Sylvester. He worked at NASA as a cybersecurity manager, and Sabia from Microsoft, Marzi from Ing, and so on and so forth. But what's most important, they have a passion for what they teach, and they actually can bring a lot of knowledge, and they're available to discuss with you what's next. So today we have Professor Maha Youssef, and without any further ado, I would like her to start her webinar about shallow and deep kernel methods.
Thank you so much for sharing this information with me. Now I will share my screen and let's start. The title of this talk is Shallow and Deep Kernel Methods, and I will discuss one real problem, which is advection-diffusion reaction example. Don't worry, I will not speak too much about mathematics. But today the main target of the topic is to answer this question. What if we don't have enough data? Because I know that now we are in an era of big data. Everyone believes that we have too much data in every aspect, in medicine, in pharmaceutical science, in data science, in business, and so on. We always have too much data. But this is not the reality in every application. In some industrial application and in some medicine application, we don't have this case. Sometimes we have really lack of data. We have shortage of data. We have few number of data. And this will not help us to design the machine learning. Let me give two fast examples of this situation that I faced in the last 5 years. The first example in chemistry, for example, this catalytic reaction experiment, and this exists almost in everywhere. For example, in the filter in your car, you need such kind of data. And here we can have the experimental data, but we have time restriction. And this time restriction saying that for one new experimental data, you need at least 2 weeks. So if you would like to design a machine learning over these data, The question is how many years you can wait. So we have here experimental data available, but we have what's so-called time restriction. You cannot wait all of these years to design a machine learning. The second example, and I faced it by myself, and it was really hard. Some experiments cannot be repeated. For example, in medicine, we had once a situation that we have real data, and this real data coming from neurosurgical department in one of the hospital here in Germany. And the situation is they have certain disease of one nerve problem, and some of these symptoms, with time, it is improving and the disease is under control. But with some other patients, this is somehow escalated, and these patients need operation. They don't have really clear criteria why these patients improve and why these patients need operation. They don't have criteria for that. They're just waiting for the improvement or not with the patient symptoms. The second problem for them, after the operation, some patients improved the symptoms and some patients not. And their question is, can we design a machine learning that predict based on some given data, which is the health measurement of the patients like diabetes, blood pressure, all of the blood scales and so on, and their scans of the brain and all of these given data, can we predict if this patient will need an operation or not? Furthermore, can we predict if this patient can heal or not after the operation? It was really a great project, but we have a small problem. We have only a data for 500 patients over 10 years or 20 years from all over Germany. We cannot add one more patient more. So this was really a challenge. We cannot make someone sick to collect more data. So in real life, I know that everyone believes that we have always big data from the business, from the social media, and so on. But in real life, sometimes we really suffer from shortage of data. And now we have to go one step further and add our own data. And this is the first challenge. Okay, how can we do it as a mathematician? Our first step is to model this problem as a mathematical or physical model, and then solve it, what's so-called simulation, solve it numerically, and get simulation solution for millions of data as you like. So you have now the experimental data, which are few, it's okay. And you have also the simulation data, which you can create as you like. Now, if you combine both, we call it hybrid data. And by hybrid data, we mean some of them are real from experimental and some of them coming from simulation. Okay, it seemed really a brilliant plan. So what is the problem? There are two serious problems. The first one, I will not go within it, which is how to model. This is not the topic of today, but the main problem here, okay, you model the problem as a mathematical problem. Can you guarantee there is a solution or not? This is the first challenge. Okay, let's say we will go to numerical simulation, which means that we are in the land of approximation. So I will solve this problem approximately, and I will accept this little error, saying that some data better than nothing using this approximation. Perfect. So you will approximately solve this equation and give this simulation solution. My second question that I will answer today, can you afford this solution? Can you afford this simulation? What do you mean afford? Some numerical solutions need that you are using really high performance computing unit. And sometimes you don't have this facility. Sometimes all what you have is your little laptop, or even sometimes you are designing this data or machine learning to put it as an application in your mobile later. So we need now to answer this question: can you afford this solution? And if my answer is no, how to design a solution that you can afford? In other words, I will design two stages of solution. And by the way, they are the same stages I will use later in machine learning. I will use a stage that I can perform, I can get a high accurate solution, and I will call it offline. And this offline that I can put my hand in any computational unit to calculate this solution. And then in the online stage, I will use what's so-called reduced solution. That is a small solution that does not need all of these computational resources, and it will give me an acceptable error. And later on, I will put also the same concept on the machine learning. Can I design a machine learning that is give me the optimal performance using a small number of data or not? This is a challenge today. Not only to get the simulation, because in all the books, when they said, okay, we run the simulation and we get the solution, sometimes people think, okay, this is really easy. Sometimes this is the most challenging step in getting the data, because the simulations sometimes need really, really high performance computing units that is not available to everyone. So the challenge now is not only to design the machine learning based on this small number of data, the challenge is to get the data first. So this is, would like to be clear that this is the target of this talk, that how to get the data cheap, how not to be expensive. And by expensive in mathematics mean always, always computational resources. So my talk today will be 4 parts. The first part, I will give foundation of kernel methods. It is like neural network methods. I will discuss what are the kernels, what is the difference between shallow and deep, and the greedy optimal algorithm with the conjunction with kernel methods. And then in the second part, I will discuss the mathematical and computational model as an example. Don't worry, I will not put any heavy mathematical notations here. I will just give you the two main concept, which is full order model, which is full order solution, this expensive one, and how to transform it to reduced order model, how to transform it to this small solution, which is a cheap one. And then in the third part, I will design a machine learning using this full order and reduced order, and to solve one of the famous problem in fluid mechanics. I will give introduction to this, and then I will give you some results about the error and so on. I will not only predict solution, but I also predict the error. Finally, I will give you like an overview of all the software that is used in this contest, how there are software for this full order model, for reduced order model, for this, all the neural network and machine learning design in this talk. So let's start with the first one, foundation of kernel-based learning. So what is kernel? Every time I would like to say kernel, I would like you to remember the neural network. So kernel method is simply non-parametric machine learning that is really operate in high dimensional. The only difference between kernel method and machine learning that instead of using explicitly mapping of a data, we use kernel functions to compute the similarity between the the inputs. So mathematical notation, a kernel is a function between the inputs, and this function measure similarity between these two inputs. I would like just to show some of the famous kernel, Gaussian kernel, which is based on Gaussian function, or Wendland kernel, or this is just well-known functions in mathematics. And the point is, it is like a neural network. Let me go here. It's like a neural network. We have input, we have output, we have layers. But in neural network, we have this function, which is activation function. We have bias, we have all of this stuff. Here we are mapping using the kernel. So from the input to the first layer, I apply kernel function. From the first layer to the second layer, I apply kernel functions. And these kernel functions are chosen carefully from a space of function in mathematics called the Hilbert space. And let me say some mathematics here. Hilbert space is allowing some features to function concerning the differentiability and integrability of these functions. And if you remember the background of the machine learning, such kind of features are needed to find the optimal design of the machine learning in this process of optimization of the error, finding the minimum error. This means that we are choosing our functions really to help us also in this process of optimization. And what we are doing that we are applying function after function after function and so on. And the question that I would ask to myself and you now, in neural network machine learning, normally we choose one activation function and we apply in all. The question is it the same in the kernel? So I choose one kernel function and it will continue with me for from the first layer to the last layer till I get the output. Actually, we can do that, but in this case, we have what's so-called shallow kernel. Shallow kernel means that we are exactly parallel to what we have in neural network, that we have fixed kernel function, and this is the problem is you do not adapt to the data structure, but you are exactly doing what you are doing in neural network. It is simply simple, it is analytically tractable because of the domain of the functions we are choosing from, and this is guaranteed, as I say, because I choose it from a well-defined space of function in mathematics. But the problem is we have a problem of lack of feature learning, and this is really horrible in adapting in high dimension. The more logical choice is deep kernel method. And by deep kernel method means we are choosing for each layer a different function. And let me back to this one now and to explain it here again. Here, in this case, we have what's so-called here, we have the input, and we apply the first kernel, and then we have the first output, and then we apply a different kernel. After all, I will end up like I ended up with composition of all of these functions. It's like I applied one function from the input to the output, but this function are is a composition of a different kernel functions. And now you can choose these new functions like you are learning from the one layer before. So you can choose these new functions like you are training over the new input. And we call this one structured deep kernel network. So this is just deep kernel networks mean this is a neural network that you are using kernel functions, but in each layer you have to use a different or two similar, but you are adapting after each layer a new one. So this is just one small example how we run these deep kernel method to fit some of data, and you can see that the data are not in one class or whatever, and we have really good results. So the main idea of the deep kernel that you are designing something similar to a neural network, but between each layer and another I have a kernel function, and it is like I mapped after all the input to the output via a continuous composition of kernel functions. Okay, so if you would like just to compare between them, you can see that in a shallow, you fix the kernel, but yes, you fixed it, this is so easy and so on, but the feature learning is so bad. The deep kernel, and this is the most important one, is easily scalable to big data. And also, the adaptation to structure exists in the deep kernel. And in the practical flexibility, deep kernel is better because in each new layer, you are starting a new learning process and you can change your kernel. Okay, now you said that you are tackling the problem of few number of data. You don't have that much data. And even when you have simulation, sometimes this simulation is so expensive and you have to carefully design your network using this kernel or even the normal network. And the best solution is to use not too much data to give me high performance. And this is what we will do here. We will do this kernel network, this deep kernel network, but we will use with it what's so-called greedy algorithm. And the greedy algorithm in mathematics, this is an optimal algorithm that is allowing you, let me explain it this way. Assume you have a machine learning that is using, for example, 1,000 data to give you performance of, for example, 70% accuracy. And the question I would like to answer here, if there is a subset of these training data, 1,000, for example, 100 or 200 input data, such that I can train this machine learning and get the same accuracy at the end or not? This is a question that greedy algorithm is answering. It is giving you the optimal subset of training data to get almost the same performance of your machine learning. Because now we are interacting with the training data, because before we have just create these training data blindly and then we feed them to the machine learning. I don't want to do this. I would like to train the machine learning over few number of training points, and then I create by the simulation one more point and I feed it to my machine learning and test the accuracy. If this point is increasing the accuracy, I will add it to my training data. If this point is not increasing the accuracy, this means that this input point, this training point, is not affecting the performance of my machine learning, and I will throw it away. And again, I will create just one. So I create under the demand. I'm not creating blindly 100,000 of points or 200,000 of points, and then I check the accuracy. I put the accuracy pre the running of the machine learning. I put a target error. I will run my machine learning with a target error, not less than whatever accuracy, 7% or 80%. So I have a target error and I would like to reach, but I don't want to reach it blindly. I would like to select point by point the optimal set of training data to end up, instead of using 200,000 of data to get me this 70%, I would like maybe to use the optimal subset of these training data, 200 or 300. This is what is greedy algorithm is doing. Again, I will not go what is the mathematics behind that, but this is the idea. The idea is to build efficient surrogate model, to build using small training points. We call it informative. Informative, what is matter? All of these 200,000 really affect the performance of my machine learning, or really there is an optimal subset can give me this the best performance of my machine learning. This is called FACOGA. FACOGA is the same deep kernel method, but we are adding this greedy algorithm. And there is a software of this, don't worry. So we put an error target and we keep adding points and so on. The advantage of this, sure, this is fast because I'm not creating blindly thousands and thousands of data. optimal convergence because you can put the convergence rate you would like to have with a fewer training points because you are choosing only the point that it will help you. You will not choose more, trash points. And this is easily adaptable to high dimension. And this is get already from the, because it is deep kernel, not because it is a greedy algorithm used. Okay, so we know now that we can design a good machine learning, a good neural network, a good network to train my data based on not too much data. Now, how to create this not too much data? Let me discuss one of the models, and this is called reactive flow. And this is one of the Navier-Stokes equation that is explaining the movement of any flow. For example, the one here, it is explaining the flow inside the pipe. Okay, assume you have a flow, and you can think about any flow, like the flow in the pipe in your car, the flow in the filter in your car, and so on. In this case, we have diffusion and we have reaction. Okay, such kind of problems, really in the experimental science, you can really collect few experimental data about that. But if you made a model like that, this is one of the forms of Navier-Stokes equation. Surprisingly, it has no analytic solution, but it has really high performance numerical solutions. I will back to these conditions again. But one of the high performance solution is finite element methods, and one of the most famous techniques in numerical analysis to solve model equations in partial differential equations or industrial equations and so on. This finite element method is just meshing the domain or discretizing the domain and it getting really almost perfect solution. But for large number of parameters, if you have really high so many parameters that you will feed to this equation like you are feeding to your machine learning, we have really a problem because of each simulation we have hundreds of megabytes to terabytes that can be used. This is what I was saying, expensive. And this is, we come into the question, can you afford to recompute this quantity of interest you would like to have? So if you made a little change of any parameter, you will repeat all the calculations again. So this is almost a perfect solution. And there are many libraries, and I will give you one of the software outside to use this one to solve this differential equation and to get the solution. But can you afford it? Do you have really a computational unit to help you in that? And if not, what, you will stop work or what? This comes to reduced order model. And in reduced order model, I would like to think like a reduced solution, like little solution. But as we choose in Fukuoka, the optimal set of points, I would like also here to choose the optimal reduced solution. How is that? I will use greedy algorithm again to say that, okay, if you have this full order model, if you have full solution, can you get another reduced solution such that the error between the reduced solution and the full solution is really acceptable to you? So again, you will put the target error before you start. And for every this full order model solution, you will find the reduced solution such that this reduced solution you can use later with a certain error 10 to the power negative 10, 10 to the power negative 11 that is somehow can be neglectable. Okay, but we have a problem here now. We are using the full order model. You have to. So what is this? I use a full order model to create a reduced order model. So I didn't avoid this step of full order model, yes, but I created this system which is called offline online calculations. How is this? Offline means I have this all of these computational units in my university in any computational resources, and I will create this full order model. and I will use it to create this reduced order model. And this reduced one that I will use it later online. And this is the same concept we do with the machine learning. In the machine learning, we create all of these set of training data. We train my machine learning, all of this offline. Offline mean I'm using all the computational units in resources I can put my hand on. But later on, when I hand this machine learning to people to, for example, in mobile applications and so on, they did not do the work I did on my computer on using this computational unit. They do only the online part, which is in this case, this reduced order model. So I will create this full order model, and then using this, I will create a reduced order model. Later on, I will hand this to all the people that it will use a later computer like that, or it will even program it in their mobile to use. And this full order model, yes, we hope that for every problem we can do it, but as we said, it's so expensive. But this reduced order model, this reduced solution, is really compress the solution to a little thing that is so fast to evaluate. So if I told you this problem has this little solution and I give it to you, you can easily program it to your computer or to your application mobile later. Okay, so now we know that we can design similar to a neural network that it can use really few input data. Second, we learn even with this highly complicated mathematical models that is really so expensive to create this full order model. Somewhere in the world, some research group in mathematics created this full order model, and from this they created the reduced order model and they gave me a faster evaluation to create my simulation data. Now, can we combine these two information together? We have a really mathematical model. I will back to this and explain it again. And I have reduced order model and I have this kernel neural network. What kind of calculations we come back to? So let me back to this is this model again, and I will explain it so we can understand. So we have a flow of a certain liquid within a pipe, and this is reactive flow. So we have diffusion and we have reaction. This is the two parameters we have. So we have only two parameters in this case. And we have what is so-called boundary, and this is special conditions. So conditions related to the place. You are giving me condition on the flow at the beginning of the pipe and at the end of the pipe. And initial conditions mean at the beginning of the time. When someone saying initial condition mean at the beginning of the experiment when the time is 0. And here is the boundary conditions and initial conditions. Again, as I promised, I will not go deep in math. But here, what is the quantity of interest I'm looking for? What is the output of the neural network I'm looking for? I'm looking for a breakthrough curve, which is simply the total mass exiting of this system over time. So you have a flow entering the pipe and coming out of the pipe. And this is so important, for example, in design of the filter in your car. You have a liquid coming and some stayed and some going through. What is going through is what we are looking for now, because it will give some impression later in some chemical conversion, but also in real life when you change your filter in your car. So I know that we can create the full order model, and then we can create the reduced one. And I would like to combine this with neural network. The first simulation that I will create the full order model using finite elements. And don't worry, there are many libraries, and I will give you examples of this today. You can do it easily online. I will use meshing of the space 100 times 100, and then I will create, using this full order model, I will create reduced one using what's so-called reduced basis technique, and you'll use only 38 basis function. And in this case also, I would like to predict the error between the full order model and reduced order model. But first, let's discuss the solutions and the error, a way of machine learning or neural network. So this is simply the solution or the quantity of interest using a full order model, and this is using reduced order model. You can see it is almost the same, and if you cannot see it, just have a look on the error. And this is the absolute error between the quantity of interest, or let's say its solution, using the full order model and the reduced order model. And you can see that this is of 10 to the power negative 11, so this is almost zero. But as I always say to my students, absolute error is not the most best criteria to judge the error. The best is to have a look on the relative error, because it gives you better impression how much this error relatively to the solution itself. And this is again 10 to the power negative 11. And this is give you really a good impression that the reduced order model is not that far away from the full order model. We just choose it smart enough to give me almost the same solution. We choose it using an optimal algorithm. Now I will, before I'm going to kernel methods, I will give just an example of a simple neural network, which is, I have 4 hidden layers with 12 neurons each, and I will use activation function reload, the most famous one. And this is again, this is the error between the full order solution and the quantity of interest, the predicted one over the test. And it's not bad. It's like 10 to the power negative 3. I will comment on this error later. And this is again using the reduced order model, and this is almost the same. And this is a prediction of the error. So I designed this also neural network, and this is somehow the trend in mathematics now. We are designing a neural network not only to predict the solution, but also to predict the errors. So without blindly predicting the data, I would like to know to predict the error in these test data. Now I will use this reduced order model solution, which is this reduced one, with Koga, which is the optimal of the kernel method, which means that I'm using few number of data with the reduced solution. Like we are in optimal 2 stages, optimal in the simulation using the reduced order model, and optimal in the network using this kernel optimal for Koga. And in this case, I will use, this is error, which is 10 to the power negative 6. And someone will tell me, it's not bad. This is something I was telling to myself at the beginning of my research. Coming from background in theoretical mathematics, we used to this kind of error 10 to the power negative 11, 10 to the power negative 12, and so on. But when I started to work in medical projects and industrial project, I remember the first meeting with industrial partner. When I get an error 10 to the power negative 3, he was so happy. And I don't know, I was ashamed that as a mathematician, I have this 10 to the power negative 3 error. This is too much for mathematician. And then he said, no, in applications, in real life, such kind of approximation, 10 to the power negative 3, or even 10 to the power negative 2 sometimes, is more than acceptable. And he got this result, and he built up later his industry on this. So when you are in a real life application, such kind of error is more than acceptable. 10 to the power negative 6, what we have here really, it is a dream. In some industrial applications, it is really dream. So what kind of software I used here? There is most of these softwares actually are free. Some of them need just a regular registration, like this one. This is Buy More. Buy More is using Python library to produce a model ordered reduction, which means this reduced based solution, this little solution. For sure, the full order solutions inside this as a first step, but you can use this library to produce the model order solution, reduced order solution. And this discretization library you can use to make the finite elements by yourself, the full order solution by yourself. This is the machine learning library, and this is the Fukuoka library. And this Fukuoka library you can find in GitHub of University of Stuttgart, and this is created by Gabriele Santin. He's an Italian guy. He was holding the same position I had later in at the University of Stuttgart, but unfortunately I didn't meet him. He left already before I joined University of Stuttgart. As a reference, the first reference is a paper that discussed already the idea of reduced order model of the pipeline. This based on a project we already worked on. And second paper for the people who like more to read about the theoretical background of deep learning. The third reference is a PhD thesis of Titian Wenzel. We already worked together in this project. He finished his thesis in 23 and he's doing his postdoc now in Munich. And this is really a brilliant thesis about deep and greedy kernel methods, the algorithm, the analysis, some applications if you would like to read. Thank you so much for your listening. I hope that it was not too much mathematics and
Thank you, thank you. There is a question for you. Someone asked, what's the most interesting project you work on using these models or methods?
actually it was partially this equation I showed you today. It was catalytic reaction. I cannot give deep explanation, but it was catalytic reaction of some chemical project that it was a cooperation between 3 or 4 universities here in Germany. And me and my team were responsible about the last stage, which is this Fukuoka and machine learning calculations.
Okay, okay. Thank you so much. And there is another one. If I like to start this course, what should I study first to be prepared for your lessons?
Which course?
Like to study, like to understand better, I suppose, how to use data as you showed here today.
Okay, first you can start by reading in these references. All of them are free references. And then
Mm-hmm.
try to start by really little given equation that my advice to you if you are a computer scientist, don't go and
Mm-hmm.
cheat the mathematical solution. You have already ready library in Python, create the solution, and then you can uh, use these ideas and so on. The software of Fukuoka, all of these software are available, so you can go around them. If you would like to go more in the math background and so on, you can find this in this PhD thesis I shared.
Okay. Okay.
Hope,
Thank you so much, Maha.
uh, hopefully it was not too much math. I tried my
Well, math is
best.
important part of the program. Thank you so much, and I will continue like with my slides. But thank you for your time here today with us.